Good. So this is part 4, which I kind of found here, and I think it's supposed to explain a little bit, the plus and the minus states. I'm curious about it. What about anything else? I mean, let's see. I'll read the summary because maybe the summary will kind of help me catch up with the other parts, which I think are going to be confused about. You know, among all these different circles, not circles, and squares and not squares and whatever. Let's see. Let's quickly remind ourselves what's going on. We have a bunch of qubits which are just like bits with values, zeros and ones, except they are allowed to do quantum stuff. Unfortunately, things happen to our qubits that we don't want. Yeah, get flipped or they get measured. Um, uh, 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 there's nothing about the actual phase flips here. The fanciness of tricks is quantum error correction. We take many of these noisy qubits, which we call physical qubits, and use them to build an almost noiseless logical qubit. So I assume an entire grid is one qubit. I mean, that's what I assume. In the toric code, we do this by putting the physical qubits on a grid that's wrapped around a torus, and imposing the rule that there must be always an even number of zeros around each white square. This still lets us have many different patterns of zeros and ones as below. When we want our logical qubit to have value 1, we use patterns like C and D. So 1, 2, 3, 4, 5, 6. Which have a big loop of ones around the torus. Or any odd number of these loops, exactly. The more loops you have, the more difficult it is for errors to happen, I guess. When we want our logical qubit to be 0, we use something like A or B, which don't have a loop like that or have an even number. Okay. An even number. Using the toric code makes a logical bit that's hard to flip. You need to flip a whole bunch of physical bits on a line to make A become C, or B become D, or anything else that's logical, so you become logical 1. It's most likely that noise won't be able to do a complete loop of bit flips, but instead it will just do some flips here and there. Then we'll usually break the rule that there should be an even number of ones around each square. So by checking the squares to see where the rules are broken, the bit flips can be detected and corrected. Yeah, I think that's kind of a good high-level summary of the other parts. The toric code also makes it hard to measure whether the logical qubit is 0 or 1. For that, we also need to use a big long loop, this time 1 going the other way. See, that's what I think I didn't catch. If we measured each physical qubit along the blue loop, we could work out whether there was an odd or even number of loops passing from left to right. And so whether the logical, okay, so you're measuring this, and now I get it. For some reason, I just didn't catch it last time. So it's simple. I mean, you measure this way because you're trying to figure out how many times this line is crossed. Like, is it even or is it like odd? You don't need to would be stupid to count these and then to count these and to count these and then to kind of keep that count. I mean, that's just a quick way to do that. We could also do it with a grid loop or a whole bunch of others. But how do you do it with a big loop? I mean, yeah, because those at the end of the day must be ones, right? So you can pick whatever measurement path you want. Even suppose that every second there is a 1 in a 100 chance that a gremlin finds and measures each physical qubit. After a few minutes, the chance that each has been measured at least once is pretty high. If the gremlins teamed up, they'd almost certainly have enough information to work out what the logical qubit is doing. Uh, that is not good enough. We need some way to keep the gremlins from getting this information. We need to be able to detect when they measure and then change things uh, around so the information is out of date. Can we do this? Um, the plus and the minus states. I mean, I don't know. Maybe so far we've always described qubits as the thing to be a 0, 1, or a quantum superposition of the two. This suggests that zeros and ones are special states and the superpositions are just weird quantum things, but that's not true. So why have we focused on zeros and ones? So one very useful thing about zeros and ones are completely different from each other. A bit or qubit can be one or the other, but it can't be neither or both. Even when a qubit is a quantum superposition of the two, it isn't really both. It's still either one or the other, but just refuses to make up its mind. Because of the different... You see, that's good. That's actually... People tend to really say the other way, things the other way around. So that's really good that this is mentioned here. Because of... I mean, that it's neither... It's not that it's both, it's that it's either one or the other, but it just hasn't made up its mind. Because of the difference between these two states, it makes sense to ask whether qubit is 0 or 1. This is a measurement that quantum mechanics allows us to make, and all the measurements we've imagined so far have used this fact. But there are other states like this that are like this, an infinite amount of them, in fact. But today we'll start looking at everyone's second favorites, the plus and the minuses. The state plus is a proposition of 0 and 1. If you had a qubit that was plus and you measure whether it was a 0 or a 1, it would randomly choose one or the other. The same is true for minus. But the types of superposition going on in plus and minus are very different. It takes a bit of math to explain this, so we won't go into more detail here. But if you're interested, check out this post where they go by the names left and right. The maths of qubits. Why haven't I found this before? I mean, it's probably now not worth reading, but maybe I'll give it a try. Seems like a rather high level explanation of the maths behind that. Aptness of S. Okay. The states plus and minus are as different from each other as zeros and ones are, and we can use them to measure our qubit. So if we have a qubit in state 0 and measure whether it is plus or minus, what happens? Well, it turns out that 0 can just be thought of as a superposition of plus and minus, so we get a random result out. We can also use them to describe the state of our qubit. Instead of saying that a qubit is in state 0 or 1, or some superposition of the two, we can say that it's plus or minus or some superposition of the two, and instead can be described in either way. Both are just ways that we can talk about strange quantum states in a way that makes sense to our monkey brains. That would rather be thinking about something simple like bananas. Neither is more important than the other, or definitely many other ways we could describe quantum states. Detecting unwanted measures. Putting this behavior together gives us a clue about how to detect whether or not gremlins are going around measuring stuff. Say we make a qubit in state plus, then go off to make a cup of tea, or while we're away, a gremlin comes along and measures whether it's 0 or 1. The qubit then randomly chooses to be one or the other. Either way, it is no longer a simple plus. Instead, it is a superposition of plus and minus. Now we come back from our tea break and want to check if everything's okay, so we measure if the qubit is plus or minus, expecting it to be plus as we left, but the result will instead be randomly either plus or minus. If we get the result plus, we think that all is well, and indeed it is. Though the gremlin made a measurement, or our qubit is back as we wanted it. Although the information that the gremlin has become the information that the gremlin has become useless by updating the state of the qubit, our measurement has made the gremlin's measurement result irrelevant. if we get the result minus our measurement has still updated the qubit and made the grandma's information irrelevant, but since it is not the plus we expected, it has also given us a clue that something dodgy is going on. We'll need to be more careful during our next tea break. Yeah, but that doesn't really... I would expect... Or is it just saying that the plus and the minus are just the same as the 0 and the 1s, but the little qubits will be pluses and minuses? So these squares would be pluses, and this would be a minus. Is that what this is saying? We can also use them to describe the state of our qubit. Instead of saying that the qubit is in state 0 or 1, some solution to we can say it's plus or minus between the two. Any state can be described in either way. Both are just ways that we can talk about strange quantum states in a way that makes sense to our monkey brain. I just read that. Good. Detecting unwanted measurements. Putting this behavior together gives us a clue about how to detect whether... I just read all that. Complementary observables. It is possible for us to make a qubit which, when asked if it's 0 or 1, will always reply 0. That qubit would simply be in state 0. It is also possible for us to make a qubit which, when asked if it's plus or minus, will also reply plus. That is, a qubit simply in state plus. But it's possible for us to make a qubit which has both properties. But it is possible for us. It cannot be certain of its answer to both questions, otherwise 0 and plus would have to be the same thing, which they are not. Any question like this, where a quantum system cannot be fully certain of its answer to both at once, are called complementary observables. Interestingly, there are very similar measurements we can do which somehow manage to avoid this, but for this we'll need a pair of qubits. Suppose we ask the pair of qubits to look at whether they are 0 and 1, but only tell us whether there is an even or odd number of ones. If we want the answer to be even, we can make them both be 0, both be 1, or be any superposition of these two. We could also ask the qubits whether they have an even number of minuses. Again, if we want to answer to be even, what if we want them to answer even whichever of these questions is asked for this? Depends so-called entangled state, which has properties Einstein described as spooky. We'll look at the maths of this more in the maths post in a few weeks. Next time we'll use the properties to add some new rules to the Turing code based on the states plus and minus. This won't disturb what we've done so far, but they'll let us detect and correct stray measurements just as we did before with B-flips. But what if a bit is... What if the qubit is like, I don't know, not in the plus state, but something half the way? That still doesn't tell me how this will be encoded. But let's see if in the next post that becomes clear. So this is just pluses and minuses will work the same. The summary is here, and the measurements is a problem. Cool.